Hi everyone, today we're going to solve this problem that is maximum average pass on lead code, which is a daily problem of the month September 2025. So let's look at this. It's a medium level problem, and yeah, let's figure out which technique we can use in order to solve this one. So there is a school that has classes of students and each class will be having a final exam. So you are given a 2D integer array classes where the first instance is the pass, which here means the total students who can pass the exam, the final exam that we have seen here, and the total number of students in that class. So just understand that we are given an information of different classes of a school, and the ith class has the information of the total number of students that will be passing and the total number of students that will be appearing for the exam. So you know beforehand that the ith class there are total this students, but only these students can pass, that is the pass of I. You are given an integer that is extra students, so this is where it gets in tricky and important. So there are another extra students, brilliant students, okay, that are guaranteed to pass. So this is important that they will pass regardless, right? So they are like pretty sharp students, and if you add them to a certain class, the total number of class students will be increased in a class, and also the pass student number will also be increased if you try to add the students from the extra students pool. Now you want to assign, right? As I've said that you want to assign and get the maximum average pass ratio across all the classes. So now they have cleared that pass ratio of a class is equal to the number of students of the class that will pass the exam. So that is the passing students divided by the total students. That is the pass ratio. And the average pass ratio is the sum of ratio from all the classes divided by the total number of classes. So few things to note here. So first of all, the average. Okay, so class ratio and the average is going to be summation of r of I upon n, and this value I belongs to n. Okay, so this is the the average class ratio. Let me write it as this average only, and the unique class ratio would be equal to the total number of passing student upon total number of students in that class. So these are the two important things to note here. Now let's try to devise like based on this, what is the average. uh, we need to make some observations first, that what is the average, based on this average class, how we can basically extract this value. So let's say that the old average, right? Average, or let's say we have first thing to note here is the old average is equal to, so this is like 1 by n, the total number of classes, and p of I upon t of I. I'll tell you why I'm keeping them as separate. And then you have all the elements from here, let's say j, that belongs to n, and j is not equal to I because we don't want to recount the the same ratio again. So this is p of j and this is t of j. Okay, this is like the first equation where we have the old average computed. Now I'll try to compute the new average. I hope it makes sense, right? That basically in this summation you would be able to see that it divides to the r of I upon n, or we can take 1 by n, or it can also be written as 1 by n summation of ri, and ri could be written as 1 by n summation of I belongs to n, and instead of ri I can say passing student by total student. So this is the same thing as we have done here. Okay, now the new average. So the new average that I will get, in this point we have basically added one student to the ith class. That is why I have kept ith as separate class. Now I'll say I have added it. So I'll say P of I plus 1, T of I plus 1 plus of the original, the all other classes, because we haven't added the brilliant student to these classes, so they will just remain as it is. P of j, T of j. Now if I try to subtract them, then I will get the delta average, which means the change in these two numbers, and that is going to be equal to, so these two equations, these two terms will be cancelled out, 1 by n remain as it is, and it is P of I plus 1 upon T of I plus 1 minus of P of I and T of I. It'll be like this, right? But one thing to note here, if you go above, this is the Ri, right? The old Ri, let's say. And here I have added one brilliant student to this Ri, and this will be the new Ri with the, let's say, if I add one to it, the delta Ri, let's take it as it is. The delta Ri will become total, sorry, the passing students, one added, total students, one added, minus passing student original value and total student. So this will be the ratio, right? Because the new ratio would be this one, with the addition of one brilliant student, total student will increase and passing students will also increase by one. If we add just one brilliant student, that's why I have set one here. Now the old ratio is going to be P of I, T of I, that is this one. So this is the delta change, right? The delta ratio change. Now, in this case, you will observe that this whole equation, if I try to substitute this part, in the later part, then you will see that this becomes nothing but delta average is equal to 1 by n delta r, isn't it? Which means that delta r I specifically, which means that the change in the average is going to be proportional to the change in the ratio, which means the gain in the ratio. So that kind of insinuates that we don't have to basically analyze the ratios for the average change. In order to maximize the average change, we should maximize the ratio change. The delta ratio needs to be maximized in order to change it. One other thing to note here, by the way, if this part is clear, then we can just go with our, the brute force that I can get in my head is that we have certain classes, you know we have certain classes, and for all the extra students, for example, if we have k is equal to 3, that is the brilliant students, we will say that in all these classes we will try to put one student in each class. Okay, their gain will be changed, isn't it? The ratio gain is now increased, and we will try to pull out the maximum gain that we can get and use it in our answer, because we need the maximum gain from the Ri ratio of I. So by doing this, the average will also be increased, and then at the later point we will realize that the maximum gain is good, and we have got all the ratios. Now let's add the all the ratios together and get the answer by dividing it by n, that is the total number of classes. Although this will cause an issue because it's very time consuming, and if you check the constraints that are given in the problem, these constraints are 10 raised to power 5, so this will definitely fail. This is like the question constraint clearly says it's 10 raised to power 5, which means they are expecting a linear solution. So this solution will fail, and the reason for that is for all the k we are trying to update the ratio or update the gain for all the classes, right? We are just doing a hit and trial method, that let's try to put this brilliant student in each the class and see which class will give us the best gain, and the best gain will indirectly give us the best average. So this whole method is, the time complexity will be very consuming. Why? Because for all the k we are doing n computations, and space complexity is as it is, let it be just n only. But this time, the worst case of this time complexity will be 10 raised to the power 5 into 10 raised to the power 5, which is basically n square, right? Which is like equivalent to n square, which will not work. So we need to optimize it. One important observation to make here, Do we really need to test it out for all the classes? For example, if we have a brilliant student, is it necessary that I need to test it out for all the classes? The short answer is no. We don't have to do it. And the long answer, that is the proof for it, is we can see that if we try to add one student to any class, let's say that this is let's say we have a delta r I, which has the value, initial value was let's p of I plus 1. Let me just not use the I anymore, it will be simple and easy for me. So p plus 1, passing students plus 1, and t plus 1 minus of p by t. If we simplify it, we'll get t minus p upon t into t plus 1. A very important observation to make here in this delta r is, in this equation, a very important thing. So if now the p value is incremented, which is p plus 1, and t value is also incremented, that is t plus 1. In this case, the new delta r will be changed, isn't it? This changed value will be t plus 1 minus of p plus 1 upon t plus 1 multiplied by t plus 2. And this will be t minus of p upon t plus 1 minus of t plus 2. Okay. So this is the point where we realize that, okay, so this is the point where we made a realization that this denominator grows, the numerator doesn't grow. So by these two equations, you realize that if the denominator is growing but the numerator is same, that means the delta of r dash minus delta of r is going to be less than 0, right? Which means the gain of the gain is going to be negative, or we can also say diminishing gaining, which means if we try to add one student, brilliant student, to a class, for example, if there is one brilliant student added to class 1, let's say, now the class 1 will give us some results, right? The gain will be, let's say, x gain. If you try to add one student again to the class 1, the gain that we got this time, let it be y, is going to be less than x. So you're getting it. The gain that we are going to have by adding a student in a class again and again will be lesser than gains that we got earlier. Why? Because of this thing that denominator is growing, and numerator doesn't grow, but denominator does. So, and also, just to give you an example of this, maybe it will be a bit more easier to understand. So let's say you have one equation that is 2 by 5. Okay, 2 is the passing students, 5 is the total students, and the ratio that you will get is 0.4. Now if I decide that let me add one brilliant student to it, this time I'll get 3 by 6, isn't it? And 3 by 6 ratio is going to be 0.5. So if it is 0.5, the change in this, the delta, is going to be 0.1, right? Now third step, let me add one brilliant student once again, and this will be 4 by 7, and 4 by 7 is going to be 0.571, and the delta in this one is going to be 0.07. But the delta 1 and the delta 2, so delta in these two, that is delta dash, let's say, this is going to be 0.07 minus 0.1. This is minus of 0.03, which means these values are decreasing, right? So the delta 1, so these delta values are basically decreasing in nature, which is why we have to make sure that we add the the new gain that we select should be maximum. That is for sure, because this is already proven in this point. Where is it? Yeah, this point. So it is already proven that the delta gain, that the gain that you are going to select has to be the maximum, because it will be added in the total average. It will be directly proportional to the total average answer that we'll get. Now the thing is, if we are always going to choose the maximum gain, then do we really need to do this hit and trial method? I don't think so, right? What we can do is, we can maybe have some priority queue in our system, and we can say that always have the maximum gain associated, always store the maximum gain. Let's say we have a priority queue, and this is going to be a max heap, by the way, because we need the max gain. So I'll say that the first element will give us the max gain. But when we have, and there are many elements like this, now the max gain is already extracted, right? We have used the max gain. After taking this max gain, the gain will change, right? And this time the gain will be less. I mean, the change of the gain will be less, but the gain will be a bit higher, but not, you know, sorry, not higher, it will be lesser as compared to the previous gain, which means we have to take it out and then push it back again, because there could be other classes where ratio gain could be more. So then we'll try to extract them and use them. And we don't have to, do an hit and try like the previous time. We have to get the gain for all the classes for each student and then do it. This time we can just put it in the queue and take it out. So this increases the complexity. This is a good solution, because like the overall complexity would be order of, for example, we have to create the priority queue, so that will be n, and log of n log n. And although there are some other operation that goes into it, but they are minimal than this one, so that is why the time complexity would be n log n for this one, and space complexity is same, because we are not using an array, instead we are using a heap. That is a priority queue, which is a max heap. So let me show you the time limit excluding one. I'm not sure if you guys are interested in that one, but let me show you this code. So yeah, here I said that we are basically, actually we don't need an array here. We can just compute it in the um, without any array, we can do that. So we just have to go through each. So for all the extra students, for one extra student, we'll get the class ratio of the current class, the new class ratio that we will able to extract, max gain that we will get, and the possible gain that I'll tell you how these variables are used. So let's say this is the class processing where we do the hit and trial, as I said. For all the classes, we are trying to see, if we add this brilliant student to this class, what gain we'll get, and if we add this brilliant student to this class, what gain we'll get. So this is the class ratio for each class and new class ratio, and the possible gain that we will get if we add the brilliant student to this ith class. So if the possible gain is greater than max gain, then max gain value will change and max gain class will be stored. So we'll try to note which class is responsible for giving us the maximum gain. Once we know that, we'll try to update that because now we know that this class will give us the maximum gain, and gain is the one that is responsible for increasing the average value. So we need to update the total students, because that one brilliant student is now added. So the total student will be incremented and the passing students will be incremented. Although extra students will obviously be decremented, or you can just optimize it, not optimize, but yeah, a bit cleaner code. And yeah, so this is how it can be done. Now the last step, we need to sum, the all the ratios that we have collected, not collected, but all the students, now we have finalized that this brilliant student should be added in this class or that class. After finalizing all the brilliant students, that where they should be added in the respective classes, now we can create and get the ratios from those classes and add them. Now we have the sum of class ratios, and we just divide it by n. So by doing this, this process, right, for all the extra student, and extra student could be k, let's say, we are doing a for loop. So this is k into n, which is basically n square here in the worst case scenario. And then we are doing a k operation again, but this is like smaller as compared to the previous one. So the time complexity will be n square, or let's say k into n to be more precise. Now the optimized one. So in this problem, in this solution, what we do is we create a max heap, right? But we do not create a max heap blindly, right? Because we need also to store the number of passing and total students that are changed along the way while we were calculating the maximum gain. So that is why we have a double array. So max heap will be created for a double array where three elements would be there. The first is the gain, then we have passing students, and then we have total students. And yeah, so now let's go through, this is the part where we construct the max heap. Let me type a comment here. Constructing the max heap, or you can also say, we initialize it. After initializing, we go through extra students, each extra student, and this time we don't have to basically search for the class, because the previous issue was that for all the extra students we need to find the maximum gain that we could have by putting them into a certain class. Now we know that the maximum gain could be easily extracted by using a login operation via priority queue, the max heap. So we'll just get the maximum gain from this one. This is the maximum gain class, by the way. We'll get the passing and total students. After we then get the gain, because this is the maximum gain that we are getting, and we need to get the new gain now, right? And that is going to be, and now we are basically adding it to the queue, right? So we are not basically doing anything, but let's assume that this extra student is now decremented after this part. After this part, at this point, this extra student is decremented. Why? Because it is being added here in this class, in this particular class it is added. So the choice of class where we were doing an n operation, a linear operation, is now reduced to log n. We just get the max value, and that's it, right? So yeah, I think it is not even login, it's constant. I might have to check that one out, because I think insertion is login, but the extraction for in a priority queue is constant. But yeah, I'll check that one out. So yes, so once we get this value, we will then add it again. Why? Because the class is not deleted, right? The total number of students is changed, the class is still there. So priority queue should be aware of the all the information of the school, that is the class, right? Then once we are done with this, we will go to the priority queue, and now this priority queue holds all the values, all the classes information with the best optimized gain. And then we'll get the because now the top values, gain values are there, but we don't need them, we just need the ratio. In order to compute the ratio, we'll just get the passing students and total students from this priority queue, that is the first and second instance of each element of the priority queue, add to the total ratio, and then we are going to return the total ratio divided by n, which is the average ratio of the entire class, of all the classes in the school. And we also are using a get gain function, where we pass just a passing students and total, and then we return the gain by dividing the by the equation that I showed you earlier. We basically, yeah, we do this operation here. Okay, so yeah, and the priority queue here is for extra students. We are just for the insertion we are doing n log n, and because it's n iteration and we are inserting it, so that is log n. So apart from that, all other complexities would be on the lower scale. So this is the priority queue this is the uh, time complexity of this solution, that is n log n. And the space complexity is also n here, because we are using a priority queue here. Although in the unoptimized solution where we were getting a time limit exceed error, the space complexity was optimized, we were not using any extra space. But n square, because this trade-off of not having an extra space but being time limited is not a good one. So we definitely prefer the one solution where we have where which is faster, right? So yeah, this is all about it. And yeah, thank you.